Hello, everybody, and welcome to today's event. This is a guide to mission control for small satellites by KP Labs. Throughout the event today, the chat function will be open if you'd like to communicate with each other. And if you'd like to ask any questions of our speaker today, Marcin, then please use the Q&A function. Although if you do put questions in chat by accident, I will see those as well. But yeah, preferably use the Q&A function, and these will be addressed as much as possible, as many as we can get through at the end of the event today. And the webinar is being recorded, and we'll send you out a follow-up message via Zoom with a link to that recording once it's processed, in order for you and anybody who any of your colleagues who maybe couldn't make it today can review the material. So yeah, just like to say thank you very much for spending time here with us today at Satsearch. We are very pleased to be able to have these opportunities to try and educate and inform the industry about important upcoming trending topics, things that you may need to know about, things that you might want to factor into your own missions. So without further ado, I would like to hand over to our speaker today, Marcin Drobik from KP Labs, and he's going to discuss with you the topic that you can see on the screen. So Marcin, please take it away.
Yeah, thanks. So, hi everyone. As being said, my name is Marcin Drobik, and I'm a head of our flight software team at KP Labs. And today I'll be talking about Oryx, which is our flight software development kit, and I'll be presenting what kind of elements goes into the software development kit that we have prepared and how you could use it in your missions. Before I do that, I will shortly introduce our company and then have a few words about maybe some kind of design decisions that were made, so you can understand where we are coming from with our design of Oryx. So KP Labs, we are a small company from Poland. We are located in Gliwice in a beautiful office building. We just 2 days ago we moved in, where we have many facilities, many labs that help us do what we do, create space missions. We currently employ a bit over 70 people from many different areas. So from many mechanical, thermal, optical engineering, through electronic engineers, through software engineers like myself, and we also have a large team connected with algorithms, with AI and stuff like that. So there are lots of people, lots of topics covered by those 70 people. We operate since 2016. We have a status of a research and development center. That means that we publish on scientific journals, and our team members are on science conferences. So if you are, for example, on this year's IAC, then you will see some of our team members there as well. KP Labs has like 4 main areas when we work with our projects and our products. We deal with images, both upstream and downstream in the imaging. So we have teams that we have projects that handle data on ground, but we also work heavily on data processing on board. We do large part of what we do is connected to software. This is what I'm talking today about, so I will leave more details to the rest of the presentation. Computing, a big part of our product line are data processing units that you can use on board to process data. And kind of supplementary to that, we deal with algorithms. So we have both like more classic computer vision algorithms to like pre-process your data, but also more modern, let's say, machine learning based algorithms that you could use on board our DPUs to process the data. But also some of the projects are for processing the data on ground. So that's a short introduction of what we do. If you will have more questions about us, then don't hesitate to contact or to ask us questions. So let's jump to Oryx. What is Oryx? The topic of our today's presentation. So as I said, Oryx is a software development kit, but that really doesn't mean a lot, right? So there are many things that can be put into SDK, software development kit label. So as I tried to kind of put it in simple sentence, I would say that Oryx is a set of tools that helps creating functionality of a flight software computer, but also helps integrating this software into mission lifecycle, and helps integrating the onboard computer with the rest of the mission. So that's a very broad definition. We have like three main categories of things that goes into the Oryx. So first of all, there's a big set of C++ modules that create the flight software functionality. So you can pick the functions that you pick, the modules, pick the libraries that you want to use, and kind of forge the final software from them. There are many of them. I will briefly discuss them also at the end of the presentation, and hopefully give you an example of how they are used. The second big area we cover are the tools that are used to both develop but also to integrate the software. And this is probably the main topic of today's presentation, actually. So I will be covering this in more detail in a minute. And the third thing is our EGSC. So this is a hardware board that is used in conjunction with the development tools and can be used also in conjunction with the C++ libraries. Okay, so before I go into the details of how you could use Oryx and what exactly tools do we have in Oryx, I just want to briefly describe like 2 or 3 major design principles that we used when we created this, and where are we coming from in that way. So I've mentioned that Oryx, especially the tools in Oryx, are handy when you want to integrate the software and the onboard computer, whatever the onboard computer is doing, right? It can be payload computer, it can be command data handling computer, whatever you want. They are handy when integrating the onboard computer into your mission. And I just wanted to give you an context of where we are coming from as a software engineers. So in software engineering, there's a term called continuous integration, which has been coined over 30 years ago. So for software engineering, that's not that, so that's a long history, right? Because from 60s to 80s, 90s, that's half of the history of software engineering probably. So if we would look at like a big project in 70s or 80s that involved many teams, many software engineers working on a single product, we would notice that most of the teams, most of the software engineers, for the most part, will work in isolation, meaning they will work on some like selected area of functionality, and then not that often they would just come together and try to launch the entire thing, the entire system with all the changes that each of them individually made. This coming together is called integration in software. It's very similar to integration you see in every engineering project. The only difference is that there is nothing tangible usually. There's a software, so it has not like physical boundaries. So it leaves each engineering team with many possibilities of integration with others. There are no restrictions really, so there are probably hundreds of ways 2 pieces of software can integrate together, which makes it, well, a bit complicated, right? And what people have found is that the longer you kind of delay the integration, the more probable is that you find some issue, some problem after the integration that will be so severe that will require to go back and kind of redo part of the work, which incurs huge like cost for the project. So in the beginnings of 1990s, people coined the term continuous integration, where it was a practice that kind of it tells that you should integrate more often. That is the simplest terms. You should build a software in a way that you kind of add the functionalities like piece by piece and not try to like build them separately and then try to put them together. So that was the heart of the continuous integration. So they started initially to do it more often, like once a week probably, and nowadays we do it every time we change something. So it's gone to very extreme. My team probably integrates 20, 30 times per day right now, even very complicated projects. So with integration comes another important thing is verification. So we have in Space, we have a phase called AIV, assembly, integration, and verification. So you have to verify the integrated stuff. Without this, it doesn't make much sense, right? So you need to, if you integrate, you need to then check if the integrated system works properly. And in software, there are very well-known instances of things that worked well in isolation, but totally failed after integration with other pieces of software. I'm pretty sure that you could bring up examples for almost every engineering field of that. And usually those failures are big. I mean, they require a lot of work. So, so by integrating more often, you reduce the amount of work that you have put to in between the integrations, and that reduces the severity of the errors that you could find because you have more continuous feedback on what you are doing. And in modern software engineering, it is considered a normal practice to have to integrate all the time and run the automated test suites all the time after every change to give a quick feedback in a matter of minutes, if possible, that you change is okay, you haven't broken anything new. And such short feedback cycles mean that you are very confident about your changes. And if you notice something, you notice it while you still have like a context loaded in your mind of the change. So the cost of fixing it is relatively low. Okay, so this is continuous integration, and as you can probably feel already from what I'm saying, is that you could actually the shortening of the feedback cycle is something you could take and just apply to other engineering practices as well. And this is more or less what's being done if you look for like lean engineering, lean production and stuff like that. It's something similar. So it's not, I'm not saying this is specific to software. I mean, the software has, I think, specific term for that. But this is where we come from. So this is one of the major design decisions, design principles that we use, is that our software should be able to support that. You should be able to work in that way with what we create. So that's one. There are two other important things, moral assumptions probably that we are coming from. This comes from our own observations from the projects that we have already participated in, both small projects for CubeSats and big for space agencies. And the first one is that hardware is scarce. I haven't seen single project that have like a plenty for hardware you could use for testing. Usually the opposite is true, at least from our experience. So when we started our mission, that's called Intuition 1, that's being launched next year. We started it 3 years ago, I think, almost 4. For the first year, we even didn't have the hardware platform to work on, to write the code for, because it was hard to get the components, and it was even before the current problem with supply chains. So that was 2018, I think. or beginning of 2019. So that's one thing. It's that the space hardware is usually very expensive. You very often work for projects that have a limited budget, and they won't be buying expensive hardware for every engineer that want to do something with it. Other thing is that the lead times for hardware, space or not space, are very long, even without the supply chain problems. So if you, for example, have like a radio equipment, it takes a long time to order it, because you have to go probably through all the legislation related to radio frequency allocation. So you have to actually create that and to be sure what radio you have to order, and this can take years really. And even if you have your hardware, the hardware you are working with your software, then you will never probably work in isolation. You will have to have other subsystems, other sensors, other pieces of hardware that you talk to somehow. And these usually are even more scarce than the thing you're working on. So I think it's quite normal in space industry, especially in CubeSat industry, that you when the FlatSat, the AIV activities are probably the first place when you have all the components on the table and you can test them. And that's very late in the project usually. So if you wait for that, that's probably not a good idea. You want to start earlier, right? The second premise we are coming from is that hardware alone is not sufficient test platform. What I mean by that is that there are many other types of tests, and you have to test on hardware, of course. Without that, that doesn't make much sense, but it cannot be the only test you are doing, because there are things you will not be able to test only on hardware. So a specific example, when you look at the usual test cases you have, generally speaking, the test cases usually have like a three areas, right? The first what you do in test case is said what is the state of the system before test. So what's the state that you are coming from? So very often, well, there are different ways of naming that. They can be like given when then, arrange, act, assert, or something. So this is the first step. Arrange your system in a specific way before you proceed with the test. Then the test has its steps, what you have to do for the test, so step by step. And then you have like expected results. So what is the observable effect of this test? And so you can kind of compare what you see, what you get, and this is the result of the test. If you are testing on a hardware, you may have trouble setting it in the correct state. So if you, for example, have temperature sensors and you test with actual temperature sensors and you want to test what happens in a sub-zero, then you will have to freeze them every time you want to test them, which is of course possible, but it takes resources and time, and it's sometimes dangerous. And then sometimes hardware will be hard to verify, right? So for example, if you have the temperature sensors again, usually they will have like a setting of how precise they are, and so how do you test if the precision is actually there? Well, if you have hardware, you can probably read it back, but that's not really going to work, right? Well, in all situations. So testing with hardware is hard because you will not be able to put it in every possible condition. So simplest example probably I should start with is testing fault detection. Right, so it's very hard to put hardware in a fault state because it's designed to not do that, right? And there are, of course, ways to inject faults in the hardware, but that's laborious, that's expensive. And of course, you should do that, but that shouldn't be the only test you are doing. Okay, so these are the two premises and the overall design goal that we want to have. So we want to shorten the feedback cycles. We want to be able to work with in a situation when hardware is scarce for us almost always. And we treat the hardware as insufficient platform for tests, but necessary. So how do we work in that context? I want to go through 5 stages of project. And this is what we do for all our projects. 5 stages of projects, and show you how our tools from Oryx toolset are kind of helping us to achieve what we want. So the first stage is that we start a project and we have absolutely nothing. We have no hardware. We only know probably we have some kind of the design, but we probably already know what kind of hardware platform we are working on. So the first thing we will start is to set up a virtual machine that emulates the target platform. So a specific example, Intuition One, I've mentioned our mission that is launched next year, uses an onboard computer for command and data handling that's based on Cortex-M microcontroller. So what we'll do, we will set up a QEMU, specifically QEMU, which is open source virtual machine, to emulate the Cortex-M architecture for us. So we can take entire toolchain for Cortex-M and start writing code using that toolchain. There is an alternative approach that uses compiling for like local PC and testing the code on like x86, x64 architecture that's common in modern PCs. However, we don't want to do this because toolchains are very there are errors in toolchains. There are errors in compilers. There are errors in linkers. You could easily misuse them. And Cortex-M instruction set is totally different than on your own local machine. There's a different width of the address bus. So there are lots of different stuff that affects how your software works. And there's no other way actually to test this to statistically use it as much as possible. So we've been using the same toolchain in Intuition One for over 3 years right now. And we are quite confident that we flushed out our important errors, and there were many of them, especially in linker. So if we just now switch to another toolchain right now before, for example, before integration, we wouldn't have this confidence. We would probably still be finding some bugs while in orbit, which is not good, of course. So we call this a single toolchain approach. So you use the same toolchain, target toolchain, the toolchain that we use to create the final flight software from the beginning of the project, because you will find some strange errors that way that you could fix on the ground before launching. So Oryx comes with a toolchain for each platform that we work with. There are Cortex-M, Cortex-Rs, Cortex-As, there are microblazes, Sparks, AVRs, lots of them. So if you need like a specific platform, you can leave the platform name in the questions, and I will try to answer what to do with this. However, QEMU actually has support for many platforms, and we currently use it as our primary virtual machine for emulations. And this is the first step we have. So at this stage, we have a virtual machine. We can run some, for example, some unit tests. We can run some simple code to verify that the setup works. Well, however, it's kind of, it has like limited capabilities because you can test probably some like algorithms, you can test some simple procedures, but your code usually will have to like control something, talk to some actuator, read some sensors, talk to other subsystems on the satellite, and right now this is not possible. So how do we proceed? So the next big thing to do, what we do in our projects is be able to write a code that is somehow communicating with other hardware. And by other hardware, I specifically mean hardware that are not part of the onboard computer that you are programming. So if you, for example, have I know, so in Intuition One, we are creating command data handling unit, which is very chatty thing. So it has to like housekeep all the subsystems on the satellite. So to write the code that, for example, monitors the telemetry from power supply, we have to have the power supply somehow. And of course, it's very hard to get. It's very expensive. So what we will do, we will write a simulator for that acts. At this, it looks from the communication protocol perspective the same as the actual device, but this will be running only on the PC. So the power supply from Intuition One, again as an example, uses I2C for control mechanism, control bus. And so what we will do, we will actually create something that has the same operations as you can do through I2C. Of course, it doesn't control anything. It just changes the flex in the memory, but we can then verify if it works correctly, right? We can then set the simulator in a state we want and see if our code reacts. So going back to the example with I made with temperature sensors, we could write a simulator for a temperature sensor and then just say, well, if you are asked about temperature, just return minus 20 degrees Celsius. And we can then check if our fault detection mechanism works correctly, because I know we should enable heaters in minus 20 or something. And now we can do that easily. And then, of course, we should then later in the project check if this is actually working correctly, but then we can repeat this test with a simulator infinity, because it's easy to do. So short example, I will try to keep the amount of code as low as possible. This is a Python code. The simulators are written in Python, so it's very easy language to learn and to use. We have like a ready API in Oryx, so you can easily define new devices that are simulated. We currently support I2C, CAN, simple GPIOs, URT, and to some extent SPI. That's an asterisk with SPI because it depends on the actual protocol, but we can do that as well. So at this point, if you have, okay, so one more thing. So in order to work this way, you have to kind of divide your code into two sections. You have to have the section that's kind of encompasses your mission. It's like the logic, you know, it's the procedures, the housekeeping, all that stuff is your mission. And you have to kind of make it separate from the actual platform that is working on. So while we are working on virtual machine on QEMU, we don't have physical I2C, physical URT. You know, you can. There are no pins that you could drive in here. So what we do is we have a ready-to-use abstractions of those peripherals that you could use to communicate with the simulators instead of driving something physical. And this is used on QEMU. So there's like a dual, there's like at least two folders in your code, right? The one with the common code that has all the mission stuff, and the second that says which interface is implemented, for example, on QEMU and which on hardware. So so at this point, we have QEMU running your code for your mission. No hardware yet. We are simulating the external devices that you communicate with. No hardware yet. We can write pretty much entire mission code in this way. Easily test all the different procedures, all the different branches you code gets in an integrated environment. Of course, you can always do that in unit tested environment, so in isolation. But here we are talking about integrating this and testing it as a whole. And you could really go far with this. However, it has no it has no like sense to do this even without running it on actual hardware. So that's the next step, running it on actual hardware. So you take your code, the logic part I've shown on previous slide, and you exchange the drivers for a physical driver. So now you say, okay, I2C, you are actually an I2C, you will drive some pins on the microcontroller when asked for read or write. And you should be able to put it on your hardware platform. And now you are in a big trouble, right? Because you wrote a code that's very chatty, that likes to communicate with other devices. And now you only have your hardware platform, and you probably don't have all the devices around you. You don't have all the sensors, although you don't have like EPS or something. You just have your platform that runs your code. So what do? Well, we already written the simulators. Why not to reuse them? And that's exactly what Oryx does. So if you write the simulators with an Oryx simulator API, it actually can work with QEMU, but it also can connect to our EGC I mentioned before, the Oasis. So Oasis connects to the PC with a USB cable. And on the one side, and on the other side, it has a PC104 connector for all the standard CubeSat interfaces. So on the image here, you can see actually the setup we have in Intuition One. The bottom left board is the Oasis board. You can see the USB connector here, and this is the engineering model of our onboard computer for Intuition One. So Oasis is like a bridge between the Python simulators and the physical peripherals of the onboard computer. So it kind of captures the I2C, captures the CAN, GPIO, UART, SPI, and serves, in this case, it serves as a slave. So if OBC wants to read something, for example, from temperature sensors, it will create an I2C transaction that will be captured by the Oasis. The transaction will be sent to the same simulator we have already written for QEMU. The answer will be generated, translated again back to I2C response, and sent to the OBC. So from the OBC perspective, it looks like it's talking to real hardware. It does talk to real hardware. However, there is no. It only talks to Oasis. The only difference are timings. Going back and forth to PC costs you some time. So as long as you are not in the real-time domain, this will work pretty well. For real-time domains, you could actually put the code directly on the Oasis. That's a custom work, but it can be done. For most cases, this is not a big problem. So right now we are in a situation when we have our hardware platform that we are writing code for, that we can write entire our code, we can run on it, even if it connects to the different devices. And if your hardware platform is similar to the flight platform, so if it has like the same peripherals, it uses the same memory map, etc., then in fact, you are already using your flight software in here. There are no differences. In this case, in Intuition One, the engineering model of the onboard computer, the only major difference is that it's lacking the GPS, which should be here, because it's like a military-grade GPS, and we only have like I think one currently, so it's just lacking it. But from the code perspective, you have access to everything. Just GPS is silent. That's all. So actually the code we are putting in this engineering model is exactly the same code that will be flown next year, hopefully. Okay, so that's important part. There are no flags. There are no flags to switch if you are switching between engineering and flight software. If your engineering model is close enough to the flight thing, and by close enough I mean it only has to have the same memory layout and the same peripherals, then you could use the same code. You don't have to like, for example, disable EPS monitoring because you have no EPS. Well, you have the simulator right now. You can use this. So the next step is when you start receiving the actual hardware that connects to your onboard computer. So example, in Intuition 1, we received say the EPS again 2 years in the project. So we already were creating the software for 2 years and rest of the project. And we only then received a physical EPS that will be used on the mission. And what we did, well, and what you can do with Oryx tools is that you can now disable the single simulator on the Oasis. So say Oasis, if there's a request to this EPS on this address, just don't answer. The EPS will do that for you. And we can now have like a hybrid flat set where some of the devices are still simulated in Python, and some of them are there for you. And so what you can do with this? Well, you can again run the integrated software. You can have a step-by-step verification of each device that you're connected to, and you can verify your simulators if they work correctly as well, which is very important. If you find some discrepancy, you go back, change the simulator to behave the same way, see if you see the same results, and fix it, right? So so this way, you're not only verifying the flight software, but you're also verifying the test suite. And you end up, after this, you end up with a test suite that has been verified against the flight components and can be used afterwards. And that's why we have the fifth stage, which I think many people during the project forget, that after the launch, you will still probably need to work with the system. You know, it is normal to have some updates it is normal that during the operations of your mission, you will prepare some patches, you will prepare some procedures that you want to be able to verify on ground before executing them on an actual hardware in space. So a very common approach is to have flight spares, but this is very costly thing to do. So most of organizations I know cannot afford having a flight spare lying around for 5 years. Even if they have a flight spares, they will use it probably for another project in a year or two, or it will fail to function when needed. With this approach, you get a fully running, fully capable test environment, even without the actual flight spares, because you have verified the simulators against the flight hardware. So if you want to, for example, update your software, you want to send some patch, then you can check if on ground it works correctly. You can integrate this, run on your on ground setup with hardware model only and simulated devices. And if it's okay, you can be quite confident that it will work on the actual hardware in space as well. Okay, so to kind of sum up this part, and I'm a bit running out of time, so but this is the most important thing probably I wanted to tell, is that the big part of Oryx is about like integrating into your mission flow, into how you approach flatset, how you approach integration test, how you verify that your functionality with different devices works okay. So in what I've presented you so far used our QEMU quite extensively, which is a part of our toolchain. The toolchain also has like compiler, linker, and other tools that we commonly use, but the QEMU is the most important part. QEMU is open source project. You can actually download it freely. There is a version that we have modified a bit, and it's available publicly on our GitHub from KP Labs, so you can check it out yourself, even without using Oryx. We supply the Python simulator API, so an ability for you to easily write the simulators for your devices. If you're using devices that we already worked with, we actually have the simulators already available and can share them with you. And we have an Oasis EGSE which connects those two worlds, connects the simulated world with the actual hardware platform. But as you probably already noticed, I haven't talked about the thing that was first in the introduction to Oryx. That is the C++ modules libraries. This is the topic that we could probably talk alone for hours, because every module is a big story here. Needless to say, we have currently, I think, almost 60 or 70 modules that can be reused in the project. So okay. So the modules. What is the module? This is a C++ library. It's a static library that you can use in your project, and they provide a wide variety of functionality that you can use to create the flight software itself. So not to test the flight software, but to actually build the functionality in the flight software. And it implements quite typical functions. So we have a module that lets you build a housekeeping functionality for your software, scheduling, various communication functions. This is a big topic usually. So communications through radio, but also communications with other subsystems, for example, using CubeSat space protocol, stuff like that. We have onboard script engine that's based on Lua. So you can actually have like a limited capability of running your own scripts, your own programs, even on a very limited platforms like Cortex-Ms. We have ready-to-use file systems. So for example, if you have a NAND that you want to use, like big 4 giga, 8 gigabytes, NAND is quite common right now. We have a file system that you can use for that. There's a module for building a fault detection, and probably many others that wouldn't fit on this slide. We have worked already with different platforms, so we have a ready-to-use drivers for those platforms that are compatible with all this approach. So you can easily swap them with a QEMU implementation back and forth to do the automatic testing and to run them under QEMU and under the hardware platform. Most of our code is based on, if it needs some kind of like synchronization or queuing, it's based on FreeRTOS. However, we have OS abstraction layer in place. So in theory, it is possible to compile it against other RTOSs. However, we haven't done it. If you would like to run this on more capable platform like Linux, again, we haven't done it. This is more targeted for like bare metal platforms. We have run it on Cortex-Ms, Cortex-Rs. We have run it on Spark. We have run it on microblazes, AVRs. I'm probably missing something, but there's a lot of variety that we've already tried and be able to run it. The crucial libraries here have already flown. They have flight heritage. We use them on PWSat-2 mission. However, many of the libraries will be used for the first time on Intuition 1 and our other missions that will be flown next year. So if you want to have more details, again, let us know, and we could like probably schedule another meeting and go into much more details with that. Okay, so if we took a single module, for example, housekeeping from that picture, when I say module, it's not only a library precompiled. If of course it's a header, so you can like link it and use the code from that library. But we also provide a Conan file, so you can actually we usually host this ourselves, but you can host it yourself, host a Conan server. For those of you who are not familiar with Conan, this is a package version manager for C++ that's gaining a lot of attention recently. It's, I think, one of the two most popular package managers. So it deals with the topics of dependency management, version management, and stuff like that. And it's very convenient to use it because if we, for example, update some of the library, we can say, yeah, there's an updated library available to you. And if you are using Conan, you can just update your version in Conan file, and it will be automatically used for you. And of course, documentation, that's also a part of each package, how to use it. So just to wrap things up a bit, This is a Conan file. So this is the file that says what are the modules being used in a project. And this is a screenshot I took probably just half an hour ago or an hour ago from our Intuition One project. So you can see there are loads of different functionality being bring to this project. So the Intuition One project itself is well, it's not very small, but it's comparably small piece, and its main role is to kind of stitch together all those modules. So it says, okay, so for example, there's a scheduling module. So here's your buffer to work with a scheduler. So you will have like a limit for 1,000 entries in the scheduler and stuff like that. So the final mission code only kind of configures those modules, pulls them and configures them for your needs. So in the end, you can focus on the mission, on the science or whatever your mission is doing. And only configure the functionalities you want. Also, as just a final example, what is possible to build using all this approach and all those toolings that we provide is one of the tests that we have again for power supply integration in Intuition One. So this is the kind of automated test that we run on almost every change. No, not every change, sorry, on every push that is going to our code repository. There are few hundreds, if not thousands, over 1,000 tests that will run on both QEMU and hardware. And for example, this test will check if we trigger specific channel in the EPS, we'll actually see the power cycle of the onboard computer, and that's without actually having an EPS. And we can run this test again if we have the EPS and see if the simulator matches the behavior. Okay, that's all from me. So there is a lot of take from this, I think, and hopefully you have like an overview of what we are proposing. So different tools to obtain this flow of development and flow of integration in your project. If you need more information on the Oryx itself, we have a dedicated website on our company site. Also, Satsearch has some more details on the Oryx. There's like a PDF leaflet to download, which has probably more like technical details on what platforms are supported and stuff like that. If you wish to like schedule a demo or something, again, you can contact us. You can contact us directly through mail or through Satsearch website. And yeah, so do we have any questions that I could answer? I know I'm stretched this time a bit already.
Thank you very much, Marcin. That was fantastic. Don't worry about the time. Obviously, if people need to drop off, that's no problem. But yeah, really grateful for that. Please, guys, do let us know if you do have any questions. I do have some. If we could to kick things off. You discussed the importance of building subsystem simulators and spent some time on that. What do you do if you're building one based on a third-party unit and they change things about how it would operate, or if there's confidentiality involved, they don't want to give you all the details?
Yeah, okay. So first of all, it's normal. It's a very typical practice. So our usual flow is that when the mission has already like chosen some of the subsystems. So for example, we've chose the EPS. That's the example throughout the demo. So we choose the EPS. We receive the documentation for the EPS. You have to receive the ICD for that. You have to have the interface documentation. If you don't, you have to somehow obtain it from them. Now, of course, the ICDs are different in every case. Sometimes they are really good. We had worked with suppliers that really we've created the simulator based only on the ICD. We then received the product that was ADCS, board. We plugged it in and everything worked as told. And it was, wow, nobody believed it. So it happens. What if they change something? Well, again, we usually, if we see changes in the documentation, we will go and first make them on the simulators. Then we can run our code and see if it broke something, if not. And then we can adjust our drivers to work with the new change. We usually kind of tag, so we have like a support for different versions, but I think that's not really needed usually. But yeah, generally, if you change something, that we are in a good situation because we can kind of okay. If they change something after you've seen the let's call the flight hardware, right? I think that's the worst situation that can happen. So you have a AIV, you integrated with some version of the software, and they said, yeah, just we've dropped a new version, but it will be okay. Again, if you don't have access to the hardware to verify your simulator, then you have to be careful. But again, simulator is there to help you if you need it. But it's good to have a good cooperation with your suppliers, because very often they will give you, okay, so we have one instance in our office, so we can like kind of lend it for you even remotely. We have done such things in the past. So for example, they have a very, very similar module that didn't just have some part of the electronics that we didn't use, and they would just send us for 1 week. We just test it quickly, say, yeah, okay, our simulators are still okay, and send it back. So if you are, for example, inside EU, that's quite simple. So if we are from Poland, we had like a French supplier. It was really simple. If you have to go through customs, then it becomes a bit more complicated, especially for double use items. But it's doable, right?
Okay, great, thanks. We've got a question there in the chat asking if you've tested the system on SoCs like PolarFire and ZBoard.
Okay, so our code is somehow related to FreeRTOS, and we are mainly focused on the onboard computers that run limited hardware resources. So like Cortex M's, Cortex R's, as I said, microblazes, but the ones that doesn't run Linux. There are free microblazes, if I remember correctly. So this kind of hardware platforms. And so no, we haven't tried it, but we have run some of our. It is possible to run this on Linux. You just need to kind of. You are able, actually, you can run FreeRTOS in Linux. It's like in an executable. It's possible. It doesn't make much sense for me, I think, but it's certainly possible. However, our main target is the bare metal, really low spec microcontrollers. As an example, for PWSAT2, we were able to get to the size of the final executable to 30 kilobytes. So that's really, really small, right? And it did a lot of stuff. It maintained communication, it maintained watchdogs, it maintained like EPSs and other subsystems. So we are talking about that kind of platforms. Okay.
Okay, excellent, thanks. I wondered if you could share a couple of the kind of big lessons you learned maybe in the development of Intuition 1 and PWSAT2 as well, or just focus on Intuition 1, perhaps. Up to you.
Big lessons.
Yeah.
Okay, I will be thinking for a moment. What kind of big lessons? So I think all of what I presented is one big lesson. Actually, we have already have parts of this system and parts of Oryx before Intuition 1 was started, but we kind of have lots of lessons learned of how we can approach this starting new. And Intuition 1 was a fresh start. Right now, we are also implementing this on other missions like PWSAT3 and a few others. So so I think the general approach that you want to be in somehow not dependent on the hardware is the biggest, I think, thing, and it saved us for several times already. In PWSAT2, for example, we have a part of this approach already implemented. We had the simulators for the subsystems, And PW-SATU was a university project. They didn't have really money to keep all the spare parts. And after 2 years, we had to do a software update. And we could test this all on ground before updating, and it was great. So yeah, I think that keeping this this flow with simulators is one big lesson learned here. There are probably many others, but we will probably get too much details.
Every mission, no.
Yeah.
Every mission there are, I'm sure. And yeah, as you say, I think it's a really important point, and it's perhaps quite easy to forget that in space how reliant we are on the hardware. But whereas in terrestrial applications, you would be shocked if a piece of software was reliant on a piece of hardware in today's industry. So yeah, that's great. Thank you. And what if there are any further questions? You know, we're a bit over the time, so if there are any further questions, please do feel free to get in touch with Marcin, with KP Labs, or with us, and you have the contact details there. I just want to do a quick little summary of the event. Sorry, just going to share my screen here.
Yeah. Okay.
Yeah, just very quickly. You know, thank you very much, Marcin. It was fantastic. It was great to understand more about KP Labs flight software, and yeah, really interesting to learn about the design principles that provide a foundation for the work and the 5 stages of the project lifecycle. I think that's really illuminated and shows what's possible, even though, as you say, you keep using the simulators, you keep testing. So it's not just step by step, but and then how the tool chain works, and how best to control the flow of information in the sort of applications that you discussed, and the use cases as well in space missions. So yeah, would like to say thank you very much from us and from all of the audience today. So
yes, thanks.
And yeah, that wraps up the event, everybody. Thank you very much to everyone who attended. Just a quick couple of things before we go. For those unfamiliar with us at Satsearch, we are the global marketplace for space. And we have built an online platform with details of thousands of companies, products and services from all around the world, the space industry all around the world. If you've got any procurement or trade study requirements, we'd be more than happy to discuss and to help you find what you need in today's industry, which is, as I'm sure you are aware, fast moving, constantly changing, and is also part of the larger changes we're seeing in the global market. So more than happy to help and discuss anything you need. We've also have quite a significant content program designed to help inform and educate engineers and other people in the industry, such as yourselves, across multiple channels all across the internet. Just to mention 3 very quickly, we have the Space Industry Podcast, which is our regular show with episodes featuring companies from around the world, including people from KP Labs. We've got a weekly email newsletter where we share trending news stories, our own updates and the updates of our members. And we also have an open Slack community where anybody interested can network and discuss important topics. And we also share aspects of our news and our work. And we would be more than happy to invite you to join us on any of those platforms, and indeed any other channels where we're present. So yeah, thank you again to Marcin, to KP Labs, and we hope to, and to everybody who attended today. We hope to see you again soon. And we would like to thank you very much for spending time with us.